Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's the only way you can help me promote my channel to keep me refreshed, inspired, and energized. Also, if my videos are important to your studies, don't forget to subscribe. So, by the method of least work, determine the horizontal component of the reaction at A. Consider all effects and compare with the result by just considering bending effects. So E is 200 gigapascals, shear modulus of elasticity 83 gigapascals, moment of inertia 500 times 10 to the 6 mm to the fourth, and area is 5000 mm square. The frame is made of wide flange shape. So if the area is very high, uh, you will notice that the other effects, axial and shear, will be negligible. Even in this problem, it will be negligible. But if the area is made, for instance, 1,000, 100,000 mm square or 900,000 mm square, it will appear that the results will be identical. So this frame is indeterminate to the first degree because of the external supports. So we will select the horizontal component of the reaction that is as our redundant force. So if you sum up moments about D, you will get 135 reaction at A downward. So that is 90 times 6 equals AY downward times 4. So AY is 135. So AH is, I'll just call it AH. Then this is also 135 if you sum up forces vertical. So that is AH and we will call this DH. For our sectioning, there will be 3 sections only. One is here, the next is here, next lastly is here. So we consider forces above or below that section, above or to the left of this section, above and to the left of this section. So for the 3 sections. So if we analyze AB, it will be subjected to bending moment, shear which is equal to AH if you draw free body diagram, and axial. However, for the axial effect, it is constant. It is not a function of the redundant force EH, so there will be no axial effect in this section, just bending AH times X and shear which is equal to AH. So therefore, delta AH which is 0 equals partial of U with respect to this redundant AH, and it is equal to for the bending priority 0 to 6 AHX, the derivative of AHX with respect to H is x dx over EI. So over EI because that's the contribution of bending. So again, there is shear. So if you draw free body diagram, this is shear AH axial, which is tension, but it is not a function of AH for the axial. So just the shear. Remember the formula K, then integral of shear force, partial derivative of that shear force with respect to the redundant divided by GA, where K is 1 for this I-shaped frame. So remember, capital K is 1. So 0 to 6 AH, this is the shear force. The derivative of that shear force with respect to AH is 1 divided by GA. So that's for this section here. For the next section, this is the entire frame to be considered, and the forces to be considered will be this. So priority bending first, so it is AH times 6, then minus 135 times X. AH times 6, moment arm 6, then minus 135 times X, 0 to 4. AH times 6 minus 135 times x. Derivative of this moment equation is 6 dx over EI. So in this section, there is shear AH minus 90, tension AH minus 90 for axial. So this value here is AH minus 90. Shear, it's constant 135. So we will not consider the shear, just the axial, because the shear is not a function of EH. So plus axial force EH integral 0 to 4 AH minus 90, then derivative 1 dx over AE. So it's because axial force. Finally, for this third section, this is the body to be considered. For bending, it is EH times this distance is 6 minus x, then plus 90 times x minus 135 times 4 for bending. So plus integral 0 to 6 AH times quantity 6 minus x plus 90 times x minus 135 times 4 derivative 6 minus x dx over EI. Then for shear, there is shear force equal to AH minus 90. For axial, it's compression 135 constant, but the derivative is 0, so there's no axial contribution here, just the shear. The shear force is AH minus 90. So plus K integral 0 to 6 AH minus 90 times 1 dx over GA. So that's it for this entire frame. So remember, K is 1. So integrating each 72 AH over EI. This is, take note, K is 1. This is 6 EH over GA. This one for AH 144 AH, then for the constant negative 6480 quantity over EI. This is axial for EH, then minus 360 over AE for the constant. Here for EH, we have 72 AH, then for the constant, negative 6480 over EI. Then finally, take note K is 1. Here it's 6 EH, then minus quantity 540 over GA. So combining like terms, so we have 288 AH minus 12960 over EI for the bending. For shear, 1 to 12 EH minus 540 over GA. Then for axial, 4 AH minus 360 over AE equals 0. So to be consistent, the numerator is kilonewton meter cube. The denominator here is kilonewton, or we'll make the numerator Newton mm cube by multiplying 1000 square, because the denominator is Newton mm square for this bending. So EI is, let's just imagine that the numerator is kilonewton meter cube. So the value of EI is 1000 kilonewton meter square. So that the unit here is meter, we want here meter also. So E, 200 times 10 to the 6 kilopascals, times I, 500 times 10 to the 6 divided by 1000 to the 4th, so that it will be in kilonewton meter square. So 100,000 kilonewton meter square. For GA, 83 times 10 to the 6, then area 5,000 over 1,000 square, you will get 83 times 10 to the 6 kilopascals times 5,000 over 1,000 square. That would be in kilonewtons. So 415,000 kilonewtons. The numerator here is kilonewton meter. This is also kilonewton meter. Then this is in kilonewtons, so that makes meter. Then AE is 5,000 over 1,000 square meter square times 200 times 10 to the 6 kilopascals. So that would be 1 times 10 to the 6 kilonewtons. So substituting 288 EH minus 12,960 over 100,000 plus quantity 12 EH minus 540 over 415,000, then plus 4 EH minus 360 over 1 times 10 to the 6 equals 0. So from here, combining like terms, you get 2.912915 times 10 to the negative 3 AH, then equals, for the constant combined, 0.1312612. So from here we can solve EH. EH is equal to 45.062 kilonewtons, and since it is positive, it is leftward. Then that is considering all effects. Considering bending moment only, so we just set this bending contribution to 0. So AH is 12,960 over 288, and that is equal to 45 kilonewtons leftward for bending only. So comparing the two, we can say that in our next example involving frames, we will ignore all other effects such as shear and axial, because the answers here are almost the same. So that's it. So in the next example, we will ignore all other effects except bending for frames.